Hello, welcome back. Hopefully we have a little bit better luck today than we did yesterday. I went ahead and I wrote a couple of the word problems down for us to look at. And there's no way that I can get the camera in the screen without hitting, I think you can see a little bit of my chandelier here that's in my dining room. At the end here, it seems cut off from my perspective. It's talking about National Park. So we're talking about a word problem that compares acres of National Park. So I would suggest we pause just a little, write everything down, give yourself some workspace, and here we go. All right, the two types of linear application problems we're gonna look at. One is where you have both a fixed cost and a variable cost, and you'll see that we just have two numbers in our problem. And another one, we're gonna actually write the coordinates and develop the equation, figure out the slope, and so this one's a little bit more complex. All right, example one. A taxi charges a $2.25 fee plus a $2 per mile charge. So one of these numbers is a one-time deal, and one of these numbers is something that we're gonna multiply by every day, every hour. We're gonna look for keywords like per, each, and every. And so you can see that when it comes to a taxi and charging you, they charge by the mile. And so this is gonna be our one-time fee. So this is going to be the b in our y equals mx plus b. And this is the variable cost. It actually is going to go in for the slope, because then when we go to figure out how much something costs, if it was 10 miles, we would plug in the number 10 for the number of miles, and so on and so forth. So this is the b, and that is the m, and our equation is going to be y equals 2x plus $2.25. X stands for the number of miles. It's always good to define your variables. Y stands for the cost. When you look at some word problems in either the textbook or my math lab, you may discover that they don't use X and Y. Maybe they use, in this case, M or D for distance. That's a really popular one to use. And they might even use C in the place of Y to represent the cost. It doesn't really matter what letters you use, as long as those variables are defined. All right, how far was a ride that cost $23.25? You can tell this is a cost value. It says right there. Another clue is the $sign, and so they're giving us, in this second half, the Y value. And how far implies that they're looking for the number of miles. So we are looking for the X given the Y. So we're gonna go ahead and substitute 23.25 in for our Y value. And I'll put it right here just in the case that you can't see the bottom half of the screen. Subtract that 225 to the other side. You get 21 equals 2x, divide by 2, divide by 2. So it looks like we are at about 10.5, 10 and a half miles. If the problem had said, how much does a 20-mile ride cost? Then you would plug in 20 for the X and figure out the charge. So you just have to kind of read for the context of the question. All right, this one, I might have to erase some of this to have room. This one is, like I said, a little bit more complicated. It's a 4-step deal. We're gonna write the coordinates. Here's our plan. Oh, I don't think you can see right here. My bad. All right, I will write the steps and then I will erase them. We are going to write the coordinates. We're going to find the slope. Maybe it'll work. we are going to substitute into the point slope form, substitute into this form of a line, which we have yet to look at, and then we're going to solve for y. All right, so those are our 4 plans. You can kind of see where the coordinates would naturally form. Time will 100% of the time be your independent variable. Time is always the x. So time is always the independent variable. All right, you can call it t for time, you can call it x and make it stand for time. It really doesn't matter. But the trick to these problems is this. The very first year, you have to zero out the year. So in 2009, we're going to change that and we're going to call that year 0. That is going to be the very first data point on our graph. So our coordinates are going to go 0, 80. All right, and we will do time and how about area? Okay, and our area is going to be in millions of acres. I hope you can see that. All right, I think let me double check here. So it's going to be 0, 80. And our second coordinate, we need to adjust how many years have passed since 2009. So I'll write this again, 0, 80. And we need to adjust how many years have passed between 2009 and 2015. And so 6 years have gone by. So my second coordinate is going to be 6 years later. I am up to 84 million acres. And then it says find the slope. And when I was speaking earlier over here, I had written down that slope formula where it is y2 minus y1 over x2 minus x1. And some of this should be a review, unless it's been a really long time since you've taken a math class, and then you probably haven't done this in a very long time. All right, so here's our x1, y1, here's our x2, y2, and so we're going to have 84 minus 80 divided by 6 minus 0, and so we have 4 over 6, and if you put 4 over 6 in your calculator, you're going to get 0.67. So there's our slope. What does that stand for? It stands for every year. Think about how this on top is the acres in millions. Sorry, flipped that there. And down here we have the years. So if you think about what our slope here represents, it looks like it represents 0.67 million acres every year. All right, so my slope is 0.67. I keep forgetting that this part is off the screen. Now it says substitute into the point slope form. You have to choose a point. Look at my 2 coordinates. I have 0, 80 and I have 6, 84. Which coordinate looks easier to work with to you is the question you need to ask. And I think anytime you have a 0 in your coordinate, that's probably going to make a word problem work out a little easier. So we are going to pick that coordinate and that slope, and we are going to plug into these 3 places. We're going to put this y value in for y1, y1. We are going to put 0.67 in for the m, and we are going to substitute a 0 in for the x1. And once we have that all substituted, we're going to go ahead and solve that for y, and that will write an equation that fits this data model. So here we go. I'm going to put it right over here so I know you can see it. So it's going to go y minus 80 equals 0.67 x minus 0. You can match that up to right here. You can see where I substituted right here, right there, and right there for these three variables. Now we just need to solve it for y and we're done. So we're going to multiply this through. So we're going to have y minus 80 equals 0.67x. And then, of course, when we multiply by 0, that's nothing. And so I'm going to jump this over to the other side, add 80, and we can do that part in our head. And so there is our model there. If you want to think about this with the original variables I mentioned earlier, you can think of it like that. And so x or t or whatever it happens to be, let me erase some of these steps and clean this up a little bit. Whether you call it x or t, t stands for the number of years since 2009, because that was our year 0. And A stands for acres of national park in millions. Okay. The very last piece of our problem says predict the square acres in 2030. So now you have to, it's not hard to substitute, but you don't want to plug in 2030. That's going to give you a ginormous answer. You want to think how many years have passed since 2009, because that is your initial year, your year 0. So between 2009 and 2030, our time has been 21 years. And so we are going to plug in 21 right here, and I'm actually going to go to my calculator. Well, 0.67 is 2/3, so that's 7/14. I think we're going to get 94, but let me just check my math here. 0.67 times 21. Perhaps I should have calculated this prior. Yeah, 94 is it. So 94 million acres. All right. If you would like to try one, we can do one real quick about life expectancy. There's some even value problems in your online version of your textbook. And then I did not do either of the ones that's in the actual text part of your book. So if you want to read through some additional examples, you certainly have that option. So, sorry guys, this example has to do with the life expectancy of males in the United States, and it compares two different years. So let me just give you the highlights. In my version of the book, it is question 34. So if you need the whole scenario, you can go and read that on your own. It says here, in the year 2000, the life expectancy of males born in the United States was 74.3. And later in 2010, the life expectancy was 76.2. The females fare a little better, but at least you're going up, right? So here we go. It might be difficult because in this case, both are measuring time, but you still want the years to be your X or your independent variable. So step 1, state the coordinates. Step 2, find your slope. Use this formula right here. Step 3, plug it into that point slope form. And step 4, solve it for y. Go ahead and put it in that y equals mx plus b. All right, so my coordinates, I'm going to zero this out, which is pretty easy because it's 0, 0. So 0, 74.3. And then 10 years later, it's 76.2. I'm going to find the slope then. The y's go on top. And so it looks like that is 0.7 at 1.9 over 10, or 0.19. So every year your life expectancy is going up by 0.19 years. All right, this is life expectancy and years, time in years. All right. Let's go ahead and use this as our m. I would use this as your x1, this is your y1. So y minus 74.3 is equal to 0.19x minus 0. And so y minus 74.3 is 0.19x. Jump that to the other side and it will become positive. And there is our equation that models the data. If you want to know how to finish this up, oftentimes it will have a part B, predict life expectancy in, say, 2040. So that would be 40 years after our initial year of 2000. So if this was the follow-up that's not matching the textbook, I'm just making this up, we would plug in x equals 40. So 0.19 times 40 plus 74.3. And then I would take that to, it's going to be right around 82, I'm predicting. But let me just plug it in to be accurate. 81.9. And that's hopefully brought you success. So there's other ones to try. If you try the odd ones in your online version of your text, hopefully you have come to realize that the odd numbers, the answers are in the back. If you don't, for some reason, have availability for the answers that are located in the back of the book, I don't know why you wouldn't. It's supposed to be an entire online version of the text. You can always reach out to me. I'll take a picture of that particular section. And of course, all your homework is in my math lab, but I do give you all of those additional optional questions if you need more practice to be successful on the test. So, all right, we're almost wrapped up with 7.3. I know it takes a little bit of time to go through all of this. That's everything you need to know about lines. And then we have parts of this section that talk about non-linear functions. And it doesn't take nearly as long to discuss these. There are absolute value functions. There are quadratic functions. Quadratic. There are rational functions, everything you did in chapter 6. And I'm missing one, polynomial functions. And all you really need to know here about each of those is kind of the basic shape of the graph and what the domain of these functions would be. So, and an example of what one of these might look like. So an absolute value function is going to look like this. It's of course going to have absolute values. I think I mentioned at some point in chapter 7 the graph for an absolute value function is a V shape, so it's kind of nice because it matches that. And the domain of an absolute value function is all real numbers. So you can write it like this, or if needed, and they would spell out the word numbers. All right. There are some examples perhaps that you would look at where you would have to graph this. They don't get difficult at all, and I can go through one if you want to see me go through one at the end here, but this is the highlights of what you need to know, and I want to show you all these graphs at once. All right, quadratic functions. We're going to look at this extensively in chapter 11. A quadratic is like what we looked at in chapter 5 with all the factoring. So it might be something, I'm just giving you an example. All right, so you might have something like f of x equals something with an x squared. So like x squared plus 5x plus 6, something like that. The x squared is the key piece for the quadratic. Think about factoring quadratic equations. That's what we talked about often in chapter 5. And so you need that x squared piece. The graph is called a parabola, and it kind of mimics the bottom part of this Q here. So a very basic quadratic has that kind of similar shape to that Q. Now, of course, it can be wider, skinnier. It doesn't have to kind of match right here at the origin. It can go down. There's a lot of variations to this. All right, same with absolute values. They can be narrow, they can be wide, they can be shifted. We just hit the highlights here. The domain of a quadratic, again, is also all real numbers. Or that, just saving me having to write it over again. Rational is like what we have been looking at in chapter 6, where you might have x plus 1 over x plus 3. Rational is a fancy word for fraction, and typically we have a variable in our denominator. A rational function usually has two pieces, always has two pieces. All right, so it's kind of disjointed. It's got two separate parts. They can be here and here, or they can be here and here. All right, they're kind of always mirror images over that invisible line right here. And of course, they can be shifted and fat or skinnier, lots of variations there. The domain here does have a trick. All right, it is all real numbers. Except x cannot be whatever value that would be to make that blow up, just like you looked at in section 6.1. So if you need to go back to section 6.1, I would recommend doing that. I can look at that and go, the only value x can't be is -3, because that's the value that's going to make your denominator undefined. All right, if you've forgotten how to do that, you just set that denominator equal to 0 and figure out from there what value will cause that to be undefined. And that is exactly why there are gaps in your graph, because of that place where it's undefined. And so when you take college algebra, you explore those graphs in a little bit more detail if that's a direction you're going. In this course, we just hit the highlights. All right, a polynomial function has to have a degree think exponent of 3 or higher. Why is that? Well, if your degree is 2, it's a quadratic. If your degree is 1, we're back to the linear equation. So a polynomial function might look something like this. All right, and please don't think that when I'm giving you an example, I'm graphing that specific example. I'm not. These things are unreal. I'm just showing you what the basic graph looks like. I'm showing you what a possible example would look like, all right? So this one matches. The rest of them are not matching. All right, and so polynomial functions tend to have swoops. What do I mean by a swoop? It kind of goes like that. The higher the degree, it can have swoops that look like this, or swoops that look like this. It kind of has places where the graph keeps changing direction. And the more degree you have, the more times it has swoops. And again, the domain here is pretty straightforward. It is just all real numbers. So what you will see in your homework is it will give you an example of a possible type of equation and say which one is it. So make sure you have good notes here, and then I'll show you what I mean. So this is a real quick quiz for you. All right, so just random, there's one of each type. See if you can kind of just match it up. What type of function is it? I did include one linear. And so if you've understood my clues of how to tell what's what. All right, this one goes all the way up to the 4th degree. So that is an example of the polynomial. Here we have a fraction, x is in the denominator, so this is an example of your rational function. All of these are all real, except for this one, x cannot be -7. Here's your quadratic. This one is actually the linear. And here's your absolute value. And for whatever reason, your book kind of spends a little bit more time on this one and shows you how to graph it using a T-chart. So that kind of gives you an overview of how to tell which is which, or give you some practice. Let's graph this one because I mentioned that I would go over that with you. And I would kind of pick, you get to pick the x's. You can pick whatever you want. I would pick those, and then if those didn't work out, I would choose something else. You know the basic shape of the graph is going to be a V. Now, whether that V is super skinny, or wider, or upside down, we're not going to develop all of those things quite yet, all right? I will tell you this back number shifts you up and down. So I should expect the shift to happen at +2 and the whole V to be kind of moved up. So this is the number that shifts it either up or down. And we don't need to worry right now about all the other clues that tell us we can just use our t-chart and graph it. All right, so what do we get at -2? If I plug -2 here and take the absolute value of -2, I get 2. 2 plus 2 is 4. If I plug in -1, absolute value of -1 is 1. 1 plus 2 is 3. If I plug in 0 here, I get 2. If I plug in 1 here, the absolute value of 1 is still 1. And if I plug in 2, I go back to 4. So you should see this repeating pattern, because when we think about a V, it's got to go down and then back up again. So let me switch colors. So -2, 4, -1, 3, 0, 2, and then we go back up again. And we want to make sure we don't stop there, that we indicate that we understand this is a continual function. Perhaps my symmetry is a little off. Please forgive my homemade graph. All right, but that is the general gist of how I would, the level in which you need to graph it. Of course, if you have a graphing calculator, you can just plug that right in and have that help you, and that's fine. All right, so that's the end of chapter 7. 7.3 takes a little bit of time to go through all the different pieces, but it's relatively straightforward, and this last part here is just matching almost. So, good luck, have a great rest of your day, and that wraps up our next unit for chapter 6 and 7 together. Take care, everyone.